So we continue our lesson of quantum ensemble. Or fundamental. So as I told you, remember that what was the ensemble? The ensemble which we consider is a selection of the n system 1, 2, 3, 4, 5, 6, this up to the n. Identical systems, so mean the same system, identical systems, and we want to study quantum mechanics for that. So for each one, so K is from 1 to n. K is the label for each system. For example, system 1 system. We need to write the wave function for the system and find the wave function and define the density matrix and take the trace and all of that. So if we say K, the label for the each system, so psi chi r, I, and t is the wave function, r, I is the location vector. Psi chi r, I, t is the wave function for the normalized wave function. So we, from the beginning, we consider the wave function normalized. So the size of the vector or the length or the norm of the vector are considered as a 1. So it means that psi chi r, I, and the t squared d r, I is 1. Or from the other notation, psi k is 1. Normalized wave function for the element number k of the system, k system in the answer. Okay. So now the problem is that how you can find the wave function. So we are working in the non-relativistic regime because there is a relativistic statistical mechanical. So we are working in non-relativistic quantum statistical ensemble theory. So in this case, the IH bar partial. This is the Schrodinger equation. From the Schrodinger equation, you can find the wave function for the k element of the system. Psi k is the state vector. It's the same actually like a general vector in the Euclidean space. So as you know from in the quantum mechanics, using the completeness condition, if you have a set of the orthogonal functions, you can expand these wave functions in terms of that. So I mean psi chi t is given as a r in chi phi n. What is the phi n? Phi n is a set of normalized functions, eigenfunctions or the functions. It will be generally so. for example, this Vn can be the wave function for the particle in the box, for example, or free particle, or anything. It depends that your spectrum or your set of the function are defined in which type of the solutions. For example, discrete solutions or continuous solutions. Okay. So the starting point to write the density matrix is that to find that these coefficients here. For example, if Vn is the periodic function, we will call this as a Fourier coefficient. If this is a Legendre or Chebyshev or Hermite or any other set of the orthogonal function, the name of the coefficient will be. Generally, this is the coefficient of this series. So to find the coefficient, you know, the strategy is that you know that these wave functions are orthogonal. So
you cannot memorize.
they are orthogonal, so you can write it the phi and star, for example, phi and here volume. The volume here we show by tau. This is the delta and that. So this is the volume element. You can write it d cubic r also is the same as that. But it's better to use the d tau or d omega sometimes. dV also, the same one. So this orthogonalization condition can be used to find the coefficient here. How you will do, you just multiply both sides to the phi m star. So phi m star is psi k, and taking the integral will be sigma n phi n k phi m R and K. Because these functions are normalized, so that will be delta and m. So
A or A to B, because we have B and N
A and K. A and K. 2 and x. Phi and phi n, so we have phi m star also here. So AMK will be phi m star psi k. So if you can evaluate this integral, you will find this coefficient. Actually, what is that? The physical meaning of this is finding AMK square is the probability amplitude of finding the system K or K number K system at energy level A, at energy E. Yes? But each phi and energy, if you consider those as eigenfunctions of the Hamilton, or this is the probability of the finding the system K at the state or at the energy n. That's a complex number. So if you make a square, you will find the probability. Now I want to using these relations, using this A top, I want to back to the original equations to this. and find time evolution for A n chi. So to find that, just you need to substitute psi k here. So just replace the psi k here. So h sigma n a n chi phi n will be I h bar partial sigma a n chi psi phi n. So I need to make it more simplified. So sigma n h r n chi phi n I h bar sigma r n chi dot. Yes, because this is a function of the time phi n. So we multiply both sides of this equation to the phi n star, and then we take the integral from both sides. So by this strategy, you will find again you use the orthonormal conditions. So phi n star phi n will be the delta of Kronecker. So it will be simplified. It will simplify it to sigma and just keep it the only term which survive here is the term which you have the n. And what about the here? About the here, these elements we call it HMN. We call it these matrix elements of the Hamilton.
Phi will depend on time. Phi is not depends on time. Phi.
No. The time parameter we give to the coefficients. So here this is considered as a stationary state, time independent. So the equation which we find is d dt r and car is sigma n. M is equal to n, so how or I told you can just shift it n to m. Okay, so this equation gives you the evolution of the coefficient, or the evolution of the amplitude, the probability amplitude of the quantum transition, if you want to talk about, or probability amplitude of the finding different elements of the ensemble in the special case. The important things here is that, as I told you, is A n chi t squared was the probability of the finding the element number k, the special energy, for example, E n, or a special level of the phi n, anyway. So the sigma of all these amplitude finally should be 1, as any other quantum amplitude in the world. Now we define the density matrix. We define the density matrix using this A. We define the density matrix as a curve this is the definition of the density matrix. 1 over n, sigma k from 1 to n, and inside the sigma you have the amplitude of the finding each element in the different quantum states. For example, AK2, this, if we K3, it means that the amplitude of the finding the system number K at the energy state, for example, E2, if you relabel that to the energy or to the state of E2. Anyway. So at one time, one of the elements of the ensemble will be found at this energy, the second one will be found at another energy. Finally, at any time, you can find, at least you can find one element in one of these energies. So this is the what I say that. And this is the definition of the density matrix. And here you have the n, so n is sigma k 1 to n is n. So this is the total number of ensemble elements. So this is the density matrix. So this definition is dependent to this series coefficient A and K. So and this is actually a function of the time. This is like the density of the particle in the phase space, which we passed before we talked about the rho Q and the P in the phase space. This is like this is a quantum version of that classical work. So I want to find the time derivative of this, and I want to see that how it will be changed by the time. To do that, I needed to take the derivative from this equation ddt rho and m, or rho m and m. It's very important to check that which indexes should be the first m, sorry, m. We want to find the time evolution of this operator. So just take the derivative of that, I h bar d dt rho mn will be I h bar d dt 1 over n sigma k we take a derivative of that. A n car star dot A m car plus A n car dot A m car star. Just take each Fourier element. You know what is each Fourier element. You need just to remember this equation that phi m star psi equal to. That was the definition of the H Fourier. So I use this here, and I use this here also, but just change the n to n. So will be IH bar 1 over n sigma power 1 to n